In the last lecture, I talked about how carbon dioxide variations have been observed over the last 400,000 years, as well as how they've been observed to change over the last 100 years. And obviously the carbon cycle is critical, and how that varies naturally as well as how that varies due to human influences. So in this lecture we're going to talk about the carbon cycle, the reservoirs that hold carbon and store it, particularly the land and vegetation, as well as the ocean, how carbon moves between those reservoirs and the time that it takes for exchanges of carbon between the atmosphere in plants, the atmosphere in soils, and the atmosphere in the upper layers of the oceans. And in fact, the timescales for these exchanges and removal of carbon dioxide from the atmosphere vary dramatically, from timescales as short as 5 years for carbon dioxide to be taken up by plants, to many thousands of years for carbon dioxide to be removed long term from the atmosphere, rather than just being cycled around and around. And we talk about the carbon cycle because, in fact, carbon is cycled around between the atmosphere and plants and between the atmosphere and the ocean. So what we're going to do is look at how carbon cycles around, and it's important to understand this. And first of all, remember, we had talked about the way that the carbon dioxide concentration in the Earth's atmosphere is very different from the carbon dioxide concentrations in the atmosphere of Venus and the atmosphere of Mars. And in fact, the Earth has a much lower carbon dioxide concentration, primarily because of two very, very important factors: the presence of water on Earth, and that allows carbon dioxide to be taken up into the oceans, and weathering of rocks, as well as the presence of life on Earth, which really was only possible because of water as well, but then life has allowed photosynthesis to be taken, so carbon dioxide can be taken up in plants. And so the very low concentration of carbon dioxide in the atmosphere of Earth compared with Mars or Venus is really an indicator that life exists on the planet. And as a signature for carbon life forms, if we wanted to do an investigation of planetary atmospheres in other solar systems, in the other galaxies, then looking for a signature of depleted carbon in the atmosphere would really be a good indicator of carbon life forms. But now let's look at the carbon cycle, and this graphic is really complicated. But what it's trying to show is the cycles between, well, sources of carbon from volcanoes, which are actually quite small, exchanges between plants and the atmosphere, and this sort of rectangle up here is the atmosphere, exchanges of carbon with the oceans, and then also human emissions of carbon dioxide. Now, we're going to use a rather simpler form. This is a more complicated slide which includes more processes, but let's look at the slightly more simplified version. And the arrows in here, the arrows up and down, are what we call fluxes or transfers of carbon. They're the fluxes in gigatons of carbon per year, or billions of carbon exchanged per year between the different areas. And the rectangles, the numbers in here, are what are called the reservoirs of carbon. So what we're going to do is look at the overall amount of carbon in different reservoirs and how that's changing, and the exchange processes. So first of all, the amount of carbon in the atmosphere is around 830 gigatons at present, corresponding to about 397 parts per million. So the way to think about this is that 2 gigatons of carbon dioxide in the atmosphere correspond to around 300 parts per million. And these units are in terms of gigatons of carbon in the atmosphere. So then let's look at some of the other exchanges. Well, this is the net exchange of carbon into the terrestrial systems. And there's an exchange going in and out each year of around 80 gigatons of carbon in between the atmosphere and the ocean. So 80 gigatons going into and out of the ocean every year, backwards and forwards, but the net change is much, much smaller than that. And in fact, the net change is about 1.6 gigatons of carbon going into the ocean every year. So 80 gigatons coming in and going out, but the net change is 1.6 gigatons going from the atmosphere into the oceans at present. What about land surface changes? Well, in land surface changes, we have actually a larger exchange going into plants and coming out again, around 130 gigatons of carbon coming out of plants and going into plants and soils every year, with a net change of only 1.2 gigatons of carbon each year going into plants and into soils. And then we come and look at the terrestrial systems. Well, I should have said, actually in plants and in soils, we have 2,500 gigatons of carbon. So a much larger store of carbon in soils and in plants than in the atmosphere. And then if we look at the total store of carbon in the oceans, it's 39,000 gigatons, a much larger store again than the carbon either in plants down here or the store that's in the atmosphere. Less than 1,000 gigatons and 39,000 gigatons in the ocean. What about if we look at human emissions from burning fossil fuels? And the human emissions from burning fossil fuels are around 8 gigatons, 7.8 gigatons of carbon emitted into the atmosphere every year associated with burning fossil fuels. Now, not all that 7.8 gigatons stays in the atmosphere. A little bit less stays in the atmosphere. If we combine the amount that goes into the net change that goes into the plants and the net change that goes into the ocean, it's about around, whoops, I'm looking at the wrong number here. The uptake going into the terrestrial plants is around 4.3 gigatons. Into the oceans is about 1.6. You'll notice that there's not quite a balance here, because 4.3 and 1.6 is going to make 6 gigatons, and that doesn't quite balance this 4 gigatons that's going into the atmosphere associated with the concentration increase, and that's because there are uncertainties in the terrestrial uptake and in the ocean uptake every year. And those uncertainties are also associated with uncertainties in the amount that's emitted every year from burning fossil fuels. And notice that there's also land clearing that is not shown here, and land clearing also produces about an extra 2 gigatons a year. Now what we have to consider is, what is the time scale for cycling around between these different systems? And there's quite rapid exchanges every year between vegetation changes and between the oceans and the emissions from fossil fuels. So there's quite rapid changes between emissions of fossil fuels and between vegetation. There's slower changes between the air and the sea, with exchanges between the air and the oceans on timescales of the order of 1 year for the upper layers, well, 1 to 10 years for the upper layers of the ocean. There's also exchanges on slightly longer timescales between soils and vegetation of the order of 10 years or so. But the really long timescales are associated with the exchange of carbon going into the deeper ocean, as well as the exchange of carbon getting moved from the soils into rocks. Deep weathering of rocks can also provide a long time scale for uptake. So there's no simple single time scale. Often you'll hear people talking about, well, carbon dioxide gets exchanged every year on these rapid timescales between vegetation and plants. And that's certainly true. But if we add carbon dioxide to the atmosphere and then look at how long it takes for that carbon dioxide to be removed. Some of it will be removed and go into enhancing plant growth, and some of it will go into the oceans quickly. And then it will come out again the following year. So the long-term removal time for carbon dioxide is determined by these long timescale processes here and here into the deep ocean sediments. And these deep ocean sediments and erosion and mineralization take many thousands of years. So that means that these very long timescale processes will take a long time to remove the carbon dioxide that's being added to the atmosphere. So now let's look at these long timescale sinks for carbon dioxide. Well, one of the long timescale sinks is actually enhanced regrowth of forests. And forests are extending their range in the Northern Hemisphere, partly because of increased carbon dioxide in the atmosphere, enhancing photosynthesis, but also because of warming in high latitudes. So the warmer climate leads to a longer growing season. The higher carbon dioxide enhances photosynthesis. So if we look at forests in the Northern Hemisphere, there's been substantial regrowth of forests, particularly at higher latitudes. And that regrowth is enhancing carbon uptake, and that can lead to a reduction in carbon dioxide in the atmosphere, but obviously not sufficient to take up the human component. There's also carbon uptake in ocean waters. Carbon dioxide is dissolved or gets dissolved in water, and so as the carbon dioxide dissolves in water, photosynthesis in algae as well as changes in the ocean circulation allow carbon dioxide to be taken down into deeper ocean waters from the upper layers of the ocean. And so sedimentation of marine sediments, as well as circulation of the carbon dioxide in the ocean waters on timescales of the order of 1,000 years, can move carbon dioxide from the upper layers of the ocean into the deep ocean. Now we have to consider what might happen on long timescales and how these interactions might be affected by temperature. So let's think about how carbon dioxide and temperature interact. And we're going to talk about two different types of processes. We're going to talk about negative feedbacks. And these negative feedbacks are things that will reduce the amount of carbon dioxide in the atmosphere, enhance the removal of carbon dioxide, but positive feedbacks are feedbacks that will amplify or increase the concentration of carbon dioxide in the atmosphere. So let's look at the negative feedbacks first of all, and I've talked about some of those. Increasing carbon dioxide concentrations in the atmosphere enhance photosynthesis, and that will enhance plant growth, and that's what we talked about in the last slide, enhancing plant growth. This will cause an uptake of carbon dioxide in plants. The warmer climate leads to a longer growing season and also leads to uptake of carbon dioxide in plants. So enhanced plant growth associated with a warmer climate also reduces the carbon dioxide. And both of those will lead to more carbon dioxide in plants and will lead to an enhancement of the removal of carbon dioxide from the atmosphere. But there's only one problem. Typically, those plants or trees will die, and as when they die, they will lead to release of that carbon dioxide back into the atmosphere. So again, there'll be cycling around unless these aerial coverage of these new forests increases. There are other processes that will lead to removal of carbon dioxide from plant stores or from the ocean. And the first thing is that a warmer climate will typically lead to more wildfires. A warmer and drier climate leads to more fires. Those fires can then burn plant material, and that will lead to more release of carbon dioxide in the atmosphere. And certainly, even if forests regrow, the risk of increased fires leads to more release of carbon dioxide. The other thing is that a warmer climate leads to more microbial activity, which will lead to faster decomposition of carbon material or plant material, and that leads to more carbon dioxide released from soils as well as faster decay of plant material. So a warmer climate leads to faster release of carbon dioxide from microbial activity. It also leads to faster decay of anaerobic decomposition and can lead to enhancement in methane as well. And finally, there is a very strong relationship where the colder the water is, the greater is the solubility of carbon dioxide in the water. And the biggest reason for the changes of carbon dioxide in the atmosphere between ice age periods, when carbon dioxide in the atmosphere is low, is that in ice ages, when the water is cold, the carbon dioxide amount in the ocean waters has increased, taking carbon dioxide out of the atmosphere. And then as carbon dioxide warms up, the solubility of carbon dioxide in water decreases, there's more carbon dioxide in the atmosphere, and that's a positive feedback. The warming of ocean waters leads to less carbon dioxide in water, more carbon dioxide in the atmosphere. Now, as an aside, some scientists have said, well, we know that in the last ice age, as the waters warmed, that led to more carbon dioxide in the atmosphere. Temperatures have increased. Maybe the recent observed increases in carbon dioxide are due to carbon dioxide coming out of the ocean waters. Well, that's possible, but there are three very good reasons why that isn't the case. The first is that if the carbon dioxide is coming out of the ocean waters, it wouldn't be expected to lead to a depletion of oxygen, and that's what we've observed. If the carbon dioxide was coming out of the ocean waters, we wouldn't expect for that to lead to a change in the carbon-13 to carbon-12 ratio associated with photosynthesis. And that's also what we observe. And finally, if the carbon dioxide was coming out of the ocean and going into the atmosphere, you would expect higher concentrations of carbon dioxide in the oceans than in the atmosphere, and we observe exactly the opposite. So no, it's not the temperature changes in the ocean waters that are then driving carbon dioxide into the atmosphere. It's actually exactly the opposite. Carbon dioxide increases in the atmosphere are due to burning fossil fuels and land clearing, and those are then leading to an increase in the oceans. But the solubility of carbon dioxide in the oceans is declining as the temperatures warm. So, to summarize, there's very big reserves of carbon in the oceans and in plants and in soils, and there's very big exchanges. But the human changes are leading to long-term increases, and these human changes are, as I said before, due to burning fossil fuels and due to land clearing, cutting down forests. There are multiple timescales, and the cycling of carbon dioxide around between plants and the atmosphere, or the upper layers of the ocean and the atmosphere, is typically 5 to 7 years. But the long-term removal of carbon dioxide from the atmosphere takes thousands of years because it has to be stored in deep ocean sediments or in mineralization of carbon dioxide into rocks. This means that carbon dioxide increases due to human activity will take a very long time to be removed due to human processes. There are a number of positive feedbacks that can lead to enhancement or acceleration of the removal of carbon dioxide from the atmosphere, as well as some processes like increased plant growth that can lead to removal of carbon dioxide. But the net effect of these feedbacks in the carbon cycle is expected to be an enhancement of the carbon dioxide increases in the atmosphere. We'll then, in the next lecture, start to talk about climate change as observed and as simulated, so that we can understand the relationship between observed climate change and whether increases in carbon dioxide and other greenhouse gases are the best explanation for those changes.